You should see a PDF.
Yeah.
Okay. So I was just going to go over how to do this, because I didn't explain it obviously well enough the last term. And what people were doing is they were taking the instructions for the lab, printing them out, and then basically scrawling on top of it with a pen and turning that in. And that's, you know, that's not a good way to do a lab report. So basically we want to sort of just go over and show what are the necessary things, the things you should add, and the different ways you can present data and your discussions, and therefore, you know, the whole report. So the things that definitely should have: your name. I took the name off of this. The name, the date, the title of the experiment, an introduction or a purpose, like, you know, what is it we're trying to learn doing this particular experiment. This particular example, we were determining the concentration of an acid through titration, and we're going to do that a little bit later, by taking the concentration of a known and then using that to figure out what the concentration of an unknown is. That's called titration. So we give an introduction, and then the procedure. Now, what's important to remember here is don't write down the entire procedure, because I know what the procedure is, you know what the procedure is. We just need a summary, just like a couple paragraphs. That's it. We don't need every single little thing, like, you know, I moved the mouse on the screen to do this. We don't need to know that. Just sort of summarize it in general. And the way you should be writing these things is in past tense, and also in passive tense. Do people know what I mean by a passive tense? Does anyone know what passive tense means?
Something is acted upon?
Yeah, exactly. You don't say I did this or we did this. You say this was done, or, you know, like a 25 milliliter beaker was used too, rather than I used, and I should not be in there at all. And in the past tense. So because you're writing a report about something you already did. So give a couple paragraphs is really all you need. So then after that, we want to see some results. And so data tables are extremely important. Should be a data table in pretty much every lab report you give, which will have all your results in it. Now you could have it like this, where this person wrote it down and then just took a picture, or some other people like doing it all like in a Word format or whatever, just have it all on the computer. Either way is fine, as long as it is legible. Man, that is important. If I can't read it, then, you know, obviously I don't know how you did the experiment or what your results were. So there should be a listing for all of the things that you did. Like, you know, what was the, you know, how much mass did you add? What was the, in this instance, would be like, what is the mass? What is the volume? What's the calculated density? And it should all have the right number of significant figures as well. Okay, so, and every data table should have a title. If it's just a bunch of data, I don't know what it means. I mean, what experiment are we talking about? What are you showing me? So it should have a title. And you can see that this person very nicely highlighted each one. So that's not strictly necessary, but it's kind of nice to show what the title of each one is. Then you can show your calculations. You don't need to show all of them. Just give an example of, like, for instance, in this, we're going to be calculating density. Just give one example. You don't have to show them all of how you did that calculation. And then there will be some conclusions. Your discussion should have, what did you before, this person actually didn't even have the conclusion. So this should be something, or else you had them at the end. There's going to be some post-lab questions. There might be some pre-lab questions and some post-lab questions. Those should be included in the report. So you can see she does a really nice job of showing her, calculations and answering the question. It's nice if it's obvious what the answer to the question is. If it's a number, you could circle it or underline it or whatever. Just make it a little bit larger than the rest. Just make it obvious what the answer is. Your discussion should, before you get to the question, should be, okay, here's my results. Did it agree with what I was attempting to learn? Did it not agree? And if not, why not? That's where your discussion would really shine. If you could, because a lot of times, almost all the time, when scientists do an experiment, there's going to be some errors. There always is. There's no way you can do anything perfectly. And so if you can discuss what some of those errors might be, we call them sources of error. And it's extremely important to be able to figure out what they are in any particular experiment. Like for instance, when you're measuring the mass of something, you're probably, when you put the whatever you're measuring the mass of on a balance and it gives you a result, that's probably not a significant source of error because it's a very accurate measure. On the other hand, if you're measuring the volume of something and you're trying to measure the volume of something like in a beaker rather than a graduated cylinder that has lots of marks on it, that is a significant source of error. If you're using the wrong piece of lab equipment to do the job, that's going to be a source of error. And so if you know that and you're aware of it, write that in the discussion, okay? And then finally, any of the pre-lab questions and post-lab questions should also be in the discussion. And then that's pretty much it. So does anybody have any questions about how to write the lab reports?
We should the pre-lab and post-lab questions should be mixed in with the discussion questions, or should it be a separate section?
You can have the pre-lab questions before, like before the procedure. You can have them there, or you can have them afterwards. Either one is fine.
Okay, thanks.
As long as they're answered. Yeah.
Do you want the date to be the date we write it or the date of the experiment?
Date you did the experiment. That's, yeah. Date you did the experiment. And if you don't do the experiment the same day as the rest of us, write the day you did do it.
Oh, I'm looking at the instructions right now, but I don't really see any pre-lab questions except the one about sig figs.
Okay, then yeah, then that'd be the only one.
Oh, okay, my bad. All right, I'm tripping today.
Oh man, that's going to happen. Let's go to the one we're going to do today. So this would be, all right, so everyone see the lab we're doing today? Does that show up on your screen? Should say Chem 210 Summer 2020 experiment number 1. Everyone see that?
Yep.
All right, cool. So yeah, one couple things we're gonna learn today is, well, one, we're gonna learn what density is. What's the difference between an intensive and an extensive property? We didn't quite get to that in lecture today, but we'll go over it in the lab. And the other thing is figuring out what precision is, because we're going to be making a lot of measurements today and trying to figure out what's an exact measurement. You can see right in the very first sentence, it's impossible to make an exact measurement. Remember when I was at UCLA, we would buy instruments that were like super expensive, and the more expensive you got, the more accurate they would be. We did something called mass spectrometry, which is measuring the mass of biological molecules like proteins and peptides and that sort of thing. So the more accurately you could measure them, the better you were in trying to identify what they all were. And of course, you'd buy $250,000 instrument and it would give you this much precision, and a $500,000 instrument would give you that much precision, and a $2 million instrument would give you this much precision, but it would never be exact. It's impossible to get an exact answer to anything. And so we're always going to be making some sort of estimate when we're doing these sorts of experiments. And so one thing I wanted to point out that's going to happen all the time is, and that runs to our pre-lab question here. Why don't we just go right down to it? Here is a graduated cylinder. So you should know it's called a graduated cylinder because it's a cylinder, and it's graduated with marks to tell you what the volumes are. Now, when you measure the volume in a graduated cylinder, it's going to be really obvious to tell what the volume is to the nearest 10 mils, because we've got 10, 20, 30, 40, 50 there. Really easy to tell in this instance that it's more than 40 and less than 50. So that first number is not an estimate. That is a precise number. It is definitely more than 40 and less than 50. So I can, so for my tens, 4 is precise. Then I look in closer and I can see that it's 41, 42, 43. So you can see that they're measured, each one of these little marks is a mil, is 1 mil. And so I know it's more than 42 and it's less than 44. So 43, this is also not an estimate because I know it's not 42 and it ain't 44. So the first two numbers are not estimates. But this last digit, I don't know exactly. I mean, you could look and say that it's not exactly on the line, and somebody else could look and say it's a little bit below or it's a little bit above. That is an estimate you have to make on your own. And so in this particular writing, if you look at it, if you see that it's right on the line, and remember, anyone remember what the meniscus is? For what does that mean?
It's like the divot in the water.
I've never heard that expression before. Yeah, water's curved, and later on we're going to learn why that is. It's one of the physical properties of water. And as I mentioned before, I'm going to talk about water till you guys are just like, please don't tell me anything more about water, but it's so important. Yeah, water, because it clings to itself. Water is like one of the most powerful liquids in keeping together, that it moves up the sides of any container it's in as the molecules hold on to each other. And so you get this curved surface. If you have a really big, like you have a really big cup or something, you don't really see it as much. But if you have a very small, narrow passage for water to go up, you'll see this sort of curve. And so we always measure the volume of water from the bottom of the divot of that. And we call the curved portion the meniscus. And we always measure the volume from the bottom. And so if you think the curve of that meniscus is right on the line, you would put 0.0 at the end. If you think it's just above it, you would put 0.1 or 0.2. Now, this number, I can't criticize this number. You and I might look at the very same graduated cylinder and see things differently. If we were in the lab, one thing I would point out to you is you want to get your eye right to the level of the meniscus. If you look at it from above, or if you look at it from below, you won't, you'll get a misinterpretation. You'll see it as being too high or too low. You want to get right at eye level. And I can't tell you what you can see. If you see that it's just above the line, then you're right. I mean, I don't see it that way, but it doesn't mean that you may have better eyesight than I do. Well, hopefully you definitely do. But so this last number is an estimate. And the last number of any measurement, it doesn't matter how accurate it is an estimate. And so that number is also significant. So this number, 43.0, all three numbers are significant. So it would have 3 sig figs. The first one is known with great precision. The second one is known with a lesser amount of precision. And the third one, well, we know it's close. The third one is going to be close, but also significant because it's closer to 43.0 in our eyes than it is 42.9 or 43.1. So that last number is significant. So who wants to look at this one below and give us what they see as the volume? So here's, oops. Let's move this up and make it a little bit bigger. All right. So what would people say that measurement is?
56 milliliter.
Nope.
56.0 milliliters.
There you go. Yeah, 56.0. That's what, but other people might look at that and say, no, I don't know if that's quite, people might look at that and say that this, say that this line, this meniscus, looks a little bit lower than the line, and they'd say 55.9. And some other ones might look at it and say, it looks like it's a tiny bit above, and they'd say 56.1. Either of those is completely acceptable. You see what you see. But what you have to remember is what is the accuracy of this particular instrument? It is given in tens, so the tens of mils is completely obvious. Each individual mil has an arrow, so that should be relatively obvious. But anything else is up to you. So really, we can say that this only has 3 significant digits. That is all that's possible. 3 sig figs is all that's possible with this particular instrument. Other instruments that we use to measure volume will have 4 significant digits because there's more gradations that you can read, and there's less estimation to make between each one of them. So yeah, so the answer here would be somewhere around 56. Now, if you wrote down 56 mils, that's incorrect because that is not sufficiently precise. There should be another digit in there. Always include the estimate for the last digit, okay? If this was 500 and 600, then the answer would be 560 decimal mils, because we could then estimate to the nearest 1 mil. But in this instance, we can estimate to the nearest 0.1 mil, and that's it, okay? All right, so let's see what we're going to be doing today. So have a look. Now, when I say density is an intensive property of matter, what does that mean? Just reading that, what does that mean to you? Hopefully you've read this already. Who can tell me the difference between an intensive and an extensive property of matter?
An extensive property could be something that you can observe visually of a certain object, but the intensive is more about the substance itself.
I don't know about that. I mean, Yeah, I mean, in a certain way, I see what you're getting at. I mean, if it's something, but there's certain properties you can't see. You actually have to measure them in some way. Yeah, I mean, you could see that like silver is shiny. Silver is shiny. That is, would that be an intensive property or an extensive property? I mean, you could see that. So would that be intensive or extensive?
Extensive.
How come?
You don't have to measure that it's shiny. I'm sorry. It's been a while.
All right, well, just read the paragraph. So it says right there, a substance will have a characteristic density at a given temperature, and the quantity of the substance doesn't matter. That's the key to the difference between an intensive property and an extensive property. So what's the difference between them? So now that you look at this, the shininess of silver metal, would that be intensive or extensive? Basically, does it depend on the amount of metal you have?
It does not.
Does not. Yeah, I could have a gram of silver and it's going to be shiny. I could have a ton of silver and it's also going to be shiny. So that would be an intensive property. It does not matter on how much you have. What about the mass, though? Would that be intensive or extensive?
Extensive.
That'd be extensive, right? Because that's totally dependent on how much you have. If I have a little lump, that's going to weigh less, have less mass than a great big lump. So that is an extensive property. That changes with how much you have. Now, since we're looking at density, could someone explain why density is an intensive or extensive property?
Mass and volume are directly proportional.
So,
As mass increases, so will volume, and then the ratio between the two will be the same.
so the ratio would be the same. So does that make it intensive or extensive?
Intensive.
Intensive, right? Because it does not matter how big, like if I want to, like go back to my silver example, if I want to calculate the density of a lump of silver, I could have a lump of any size and I'll get the same result. So if I have a big ass lump of silver and I, put that into some water and I measure the mass of the silver and then I measure the volume of water it displaces, I should get the same mass to volume ratio as if I used a really small piece. Of course, I may be a little more accurate with a larger piece than a small piece, but I should get the same answer. Another one they give there is melting point. If I want to look at the melting point of like a grain of sugar, it should melt, a tiny grain of sugar should melt at the same temperature as a larger grain. And again, it may not be as accurate, but I should get approximately the same value. The solubility is another one. 1 gram in 10 mils of water and 10 grams in 100 mils of water will dissolve exactly the same. So it doesn't matter how much I have. So any other questions about intensive and extensive properties? Will you be able to tell the difference? Everyone's got it. Everyone's an expert. I love it, right out of the box. All right, here's one. Every liquid has something called a vapor pressure. That is the amount of pressure that it gives off as a gas. So we know that water is solid, liquid, gas. So even when you have ice cubes in the freezer, a tiny amount of gas is being let off those ice cubes. That's why if you leave an ice cube tray in a freezer for like a year, the ice is gone because it's all turned to gas, even though it's freezing in there. So would you say that the vapor pressure of a liquid is an intensive or an extensive property? In other words, would it be different if I had 10 mils of water or if I had 100 mils of water? Would my vapor pressure be the same?
Would it depend on the surface area?
No, it shouldn't. Good question, though.
Wait, can you rephrase the question?
Okay. Yeah, maybe I need a better example. That's a little advanced. Okay. Here's one. Conductivity. Some metals conduct electricity better than others, and metals conduct electricity better than non-metals do. You think conductivity, the ability for it to conduct electricity from one end of a wire to the other, is that an intensive property or an extensive property?
Intensive,
Why is that?
because it doesn't matter the amount that you have of it.
Right. I mean, that's not quite true because the resistance will depend on the amount. But yes, you can determine the conductivity of this amount, this amount, this amount, this amount, and it should be the same. That is an intensive property of any particular substance, and it's unique to each substance. That's another thing that we learn about intensive properties. Intensive properties are generally unique to that substance. Like, for instance, the densities that we're going to be working out today. Each metal, each particular substance, wood, ice, whatever, has a unique density. And we can actually use density to determine the identity of some things. Like, for instance, if we take a piece of metal and we're not quite sure what it is, because a lot of metals are shiny and kind of silver colored, you can't really tell one from another. But if you determine that its density is like 2.70 grams per mil, that's aluminum. That's not anything else. That's aluminum. Aluminum has that density. Aluminum oxide or some other form of aluminum has a different density, but pure aluminum has that density. That's something else that intensive properties have, that they're basically unique to that particular thing. And we use the intensive properties to identify things. So in the first part of our lab, we're going to go to this particular website. And I've also shown additional reading you can do, because it would have been the first lab we would have done in person as well. And so there is a link to the in-person lab manual in the Canvas shell. Hopefully you can find that. If you can't find that, let me know. So the first, it has some pre-lab questions. There's some other things in there that you can have a look at if you're confused about what we're doing here. So as I mentioned, we're going to use Adobe Flash, and I'm going to try and get as many Adobe Flashes out of these experiments as I can, because it's basically going the way of the dinosaur, and will be banned from a lot of computer systems by the end of the year. But for now, we can still use them. I've heard that it's sometimes a trouble to get them to run on Macintoshes. If that's the case, you may want to get the data from somebody who is able to run it. And if you have the data, you can still write the lab report. Okay. So you should get a screen like this when we enable. I'll show you how that works. And then you'll pick different, I think you have the choice of wood, ice, brick, and our friend aluminum. And this is actually, everyone remembers, Eureka. If everyone's heard of that story, like Archimedes getting in the water and like, taking a bath, and then Eureka, I've discovered it. Are you familiar with that story? Do you know what he discovered?
Nope.
He was promised a gold crown if he could basically determine whether or not the crown was made of pure gold or not. And nobody else could figure out how to do it. And he figured out how to do it because he knew what the density of pure gold was. And so if he took because when he got into the bath, he saw that the level of the bath water went up, that he displaced a certain volume of water. And so if he took that crown and weighed it, got a mass for it, and then got a volume of it, and this was the part that no one could figure out how to do, because it's an irregular shaped object. You couldn't exactly take that crown and smush it into a cube and determine its volume. The king wouldn't like that very much. So what he did was just take the crown and drop it into some water and measure what the volume of the water was displaced. So when he had a volume and a mass, he determined the density. And if the density was less than that of pure gold, then it wasn't pure. And he could pretty much figure out how much other stuff was in it. But if it was right at the density of pure gold, which he said it was, and then he was awarded a pure gold crown. So, good on him for figuring it out. So this is how we measure the volume of irregularly shaped objects. It's really hard to calculate. If you have like a rock with a really odd shape to it, it's really hard to try and figure out the volume of it. If it's perfectly round, or if it's perfectly square, or if it's a perfect cube, then it's pretty easy to determine the volume. But what if it's some bizarre shape? Well, if you just dunk it into the water and you just measure the volume of water that it displaces, that's the same volume. And so what we're going to figure out is taking a known mass of these substances and putting them in the water and seeing how much water they displace. We'll figure out what their densities are. And then this will be example of the data table you can use. You basically copy this right away if you want. What we want to introduce is the idea of doing trials. Now in the lab, you never do an experiment once, ever. And we don't do an experiment twice. Why do you think we don't do, why do we repeat experiments?
For accuracy?
That's right. That's right. Because each time we do, we can pretty much imagine the precision. We can control the precision of an experiment. We cannot control the accuracy. If we do it right, we hope that it's precise and accurate. But we know what our precision is. We don't know what the accuracy is because we don't know what the answer is. And so we do it more than one time. So why don't we just do it twice?
There's not enough data, maybe?
How come?
I guess the more that you do it, you can kind of average out like the experiment. So you have like, I don't know, you can see all of the outcomes of keep doing it and doing it, because if you only do it twice, it's not for sure. It's not like accurate or precise as how you were saying.
That's right. Why do you think 3 is better than 2?
Why do I think 3 is bigger than 2?
Why do you think it's better? Well, we know 3 is bigger than 2.
Oh yeah, sorry. I'm a little asleep.
Oh man. Someone's going to need to do their math homework a little better.
No.
Yes. Why is doing the experiment 3 times better than doing it twice?
Because if it's twice, you don't know which one is wrong.
Exactly. Very good. Yeah, we're going to be introduced to something called outliers. Now, when I worked in a lab where we looked at patient samples. So, really, really valuable samples. and we tried to measure the concentration of proteins in like blood and urine and cerebral spinal fluid or whatever it was we had. And so it's really valuable samples. And so if I did the experiment twice and got two different results, how do I know which one is closer to the right answer? I don't. You know, one of them could be way off and the other one could be exactly right. And so if I take an average of them, I'm getting a wrong answer. I'm limiting my accuracy. But if I do it 3 times and 2 of them agree with each other very, very, very well, and the third one is way off, well, then I'm going to throw away that third one. I did something wrong. Something got screwed up. My robot didn't pipette correctly or something. I ran out of one of the chemicals I was using. Something went wrong. And so I can just throw that away. And then the 2 that agree with each other, I'll take the average of those 2 and say that that's more accurate than the average of those 3 because one of them is clearly wrong. Okay, so that's why we do everything at least 3 times. Sometimes if you can do it 4 times, even better. But twice is not good enough because if you get an answer, so if we're calculating the density of aluminum, for instance, and your first answer is 2.5, which is pretty close to 2.7, but your next one is 7, and then you take the average of 2.5 and 7, you're going to be way off. But if you do it 3 times, and you get 2.5 and 2.8 and 7, well, that 7 is clearly wrong. Toss. So then you're going to take the average of 2.5 and 2.8, and you're going to be really, really close. So that's why we always do 3 trials. We just call them triplicates. Triplicates is basically, that's the gold standard for doing these. One of the labs at UCLA that I was fascinated with, I got to meet the director of, is the Olympic lab. They're the ones that do all the testing for athletes, like, you know, steroids and stuff like that. And I always thought it was called the Olympic lab because, you know, they tested stuff for the Olympics. No, it's because it's on Olympic Avenue. Duh. So it's like, oops. Yeah, so it's on Olympic Avenue. And so, yeah, they run every sample 3 times. And so they get the averages of 3 because it's pretty important. If you're going to deny someone a gold medal, you better be absolutely sure that your answer is both accurate and precise. And so if you just run it once, that's not nearly good enough, okay? So that's our table A, because we're going to be doing 2 experiments today. First one is just density of known things. And then B, we're going to be looking at the second experiment, we're going to be looking at unknown things and then trying to figure out what they are based on their density, okay? And then there's some questions. How does the density of an object help you identify it? That should be part of your conclusions at the end. And then post-lab questions. We've already pretty much answered the first one. Hopefully you remember. And then this will be part of the discussion afterwards, just giving the answers to the post-lab questions, okay? So is everyone ready to go to the first? If there's any other questions, should we try going to the first one?
Oh, I'm just
go ahead.
trying to wrap my head around writing this lab report in past tense.
Okay.
Sorry. Yeah, I'm no grammar buff, but I kind of suck at writing, so.
Well, hopefully you'll be, you'll write it a little bit better than I suck at grammar stuff.
Okay. Well, I think I'll just look it up what past tense or passive tense.
Oh yeah, passive voice. Passive voice just means that instead of writing, I picked up the beaker and added 50 mils of water, you would write, the beaker was filled with 50 mils of water.
Oh, I didn't know it'd be that simple.
Yeah. No. We try and make things as complicated as possible, but yeah, it's not that hard.
All right,
It's just
thank
that
you.
it's the way, like when you all become successful scientists and you're writing all these like fancy scientific articles and you're begging the government for money from the National Institute of Health or whatever. That's how you're going to write. Those are really important lab reports. I've had to write lab reports that were worth like $5 million. And you better be sure that I wrote really good lab reports and dotted my I's and crossed my T's and, you know, did that really, really well. Because, yeah, you're going to be writing reports for like, you know, the rest of your life if you're going to be any kind of scientist. So it's important to get relatively good at it early, and then we'll be adding more and more and more stuff to it
Thanks for
as
clarifying
we
that.
go. Yeah, no worries, man. All right, so to get to the website, we just basically go over there and hover over the line and just click, and it should take us right to it. Allow.
I have a question about grading.
Yes.
By any chance, will you be curving the first lab because it's like our first time doing it, or
No.
like you're gonna be lenient or in any way?
Nope. I'm gonna be mean and awful. I'm a mean and awful person. No, I mean, obviously the first one, yeah, it's going to be a little more lenient because you don't know what I'm looking for because I haven't graded one before. Whoa, I'm now deaf. Yes, so that's the first one, yes. But then as we go, hopefully you'll, you know, really pick up what it is we're trying to get you to do here. But generally I don't curve like for exams and that sort of thing. I haven't in the past. Basically, if I have to curve something, it means I wrote an exam so bad that either everybody got 100 on it or everyone failed it, and that's on me. So hasn't happened yet, but fingers crossed. All right, so what if people got to, I need to share the new screen. So new share, the actual screen. There we go. So you can see the screen here, hopefully. Has everyone got to this site?
Yes.
Anyone having trouble with the flash part? I know some people before were warned that, you know, they'll if they try and run flash, it'll, like, you know, destroy their computer. It won't. Is anyone having trouble getting this to open?
Mine is not loading. I have no idea why.
Not loading. Yeah, okay, so just click the reload and see what you get. What answer is it? Just spinning or something?
It's saying that it's it can't find the website. Like, you know, that classic we cannot connect to this website thing on Google Chrome. I'm not sure what's happening.
I'm using Chrome. You can always try copying and pasting directly rather than just clicking on it. You can try that.
Yeah, that one worked. Okay,
Oh,
thank you. I think
cool.
this is a
Man,
problem.
almost like I do something about computers, which I haven't in many, many years. Anyway, so here we are. And so what we're going to do is look at our four different materials and try and get density values for each one. And what I would like you to do is, let's just take that out. What I'd like you to do is use different amounts each time. Okay, so you can change the mass by just sliding on the over here. So I can use like a really small piece, or I could use a really big piece. So what you should do is try 3 different sizes for each of your 3 different trials. So for instance, really, really small would be, all right, let's say 1.26 kilograms. I'm going to pick that up and slosh it in the water. And what do you notice about the volume? Now that I've put that in the water, what do you notice about the volume that it displaces?
It goes up
By how much?
1.26 liters.
Interesting. So would you say that the density of this piece of wood is 1 because it weighs 1.26 kilograms and it displaces 1.26 liters of water.
Well, where are the units?
The units are going to be in grams per mil or kilograms per liter, either one. It's the same number. So let me write on this. Yeah, you can give them whatever units you want. So here we have a mass of 1.26 kilograms, and it's displaced. How much volume has it displaced? Now it's not 101. It hasn't displaced all of it. How much? What's the volume it's displaced right now?
3.6.
3.6? What volume of water has it displaced?
1.26.
Yeah, so the volume
6.
1.26 liters. And so we know that density is mass divided by volume. And so you can give it in grams per milliliter, or kilograms per liter. The number is the same. The units are slightly different, but the number will be the same. So if I give it in kilograms per liter, it would be 1.00 kilograms per liter. Is that the actual density?
Isn't it that it displaces the amount of water that's the same weight as the object?
Mm-hmm. Yeah, it definitely does. That's how it works. That's how boats work. That's how you can have a boat float that weighs 100,000 tons. If it displaces more water than it weighs, it will float. Even if it weighs like an aircraft carrier, I think you would agree is denser than water, right? But the way it's designed, it displaces more water than its mass. And so it floats. In this instance, it's floating. It's displaced as much mass. It's displaced as much water as its mass, but there's still more mass above the water. You notice that? What are we going to have to do to actually determine its proper density?
Pull it under.
Yeah. Let's just click on it. And we need to push it under. Now it's under the water. Notice that its mass is the same. It's still 1.26 kilograms, whether it's floating on the top or sitting on the bottom. And it doesn't matter if we have it just a little bit above, a little bit below the water, or all the way to the bottom. Notice the volume doesn't change. Once we let it above, the volume changes. So what's the actual volume of this piece of wood?
$3.16 liter.
Right, 3.16 liters. It is not 1.26 liters, because we can clearly see it has that much volume that we're not measuring. And so that's going to be true for anything that's floating. And that's one thing I noticed, like at least half the students last term missed, was that they did not push things to the bottom. And so they gave the density for anything that floats to be the same as water, which obviously it isn't, because there's more volume that we're not measuring here. So make sure you do that. So let me clear all this out. So what should be the actual determination? What number should I actually use to measure to calculate the density of this block of wood? What mass and what volume?
Would you still use the 1.26 for mass, but
Yep.
the 0.16 for volume? So it'd be 1.26 over 3.16, and that'd
Exactly.
give you.
Mm-hmm. Yes. Exactly. Yeah, my mass hasn't changed. It's still the same piece of wood, even if I'm, you know, pushing it down. It's still the same piece of wood. I haven't added any mass to it. But what I've done is completely submerge it in the water so that all of the wood is displacing water, not just the part equal to its mass, all of it. And so now that I have it, so it'll be 1.26 kilograms divided by 3.16 liters, or 1,260 grams divided by 3,160 milliliters. So you can either give it in grams per milliliter, or kilograms per liter. Either one is fine. I don't think it says, if it doesn't say which units to use in the procedure, you can use whatever units you want. But you know, use metric units. Don't convert everything to, you know, pounds and gallons. There's so many pounds per gallon, that would be hard to read. Okay. And you should get the same answer whether you use a great big piece or a little bitty piece. So let's do the same. So then you just do the same thing with, let me clear all this out of here. Then you do this, just the same thing with ice. So let's move this out and select ice. Oh, there's also styrofoam in here. I forgot there's 4 things. So let's take this styrofoam example. And you can make this as big or as small. So let's get a really big piece this time. There we go. There's a big piece of styrofoam. So when we put that in the water, you're going to notice that hardly any water is displaced comparative to the size of that block. It's because we know that styrofoam is even less dense than certain woods. Certain woods are like don't float on water because they're really, really heavy, really, really dense. And other woods are really, really light, like balsa wood you make the airplanes out of. But styrofoam is even less dense than that. So you have to take it and push the whole thing under the water. So what will we use for a mass and a volume for this one? To determine the density of styrofoam, what mass and what volume do we use?
The 3 kilograms
Mm-hmm.
for mass.
Mm-hmm. And how many, what's the volume that it displaces, the volume of water it displaces?
20.
Nope.
120.
Nope. Why don't you use this? How many significant digits would we get?
Oh, 0.0.
20.00, yes. 20.00. So if we divide 3 kilograms by 20.00 liters, how many significant digits should we get in our measure of density?
3.
Right, because we have three significant digits in the mass, 3.00. We have 4 significant digits in the volume, 20.00. And remember, when you do either division or multiplication, whoever has the smallest number of significant digits, that's what we use. So we use 3. Very good. So sorry, I interrupted you. You had a question.
No, you answered my question. I was wondering how do you know how many digits to use, but you just answered it.
Well, we can use the ones that are given right there. We assume, and when you assume, when we should see how many digits are given. So we assume those are the significant digits for that measurement. If you're given 3.0, then that's only 2. If you're given 3, that's only 1. So we would assume that if they're giving us 3 digits, there must be a reason for that. That they could. That's the precision of that particular measurement. Okay, so then you would use those 5. There's styrofoam, wood, ice, brick, and aluminum. And I think the particular the experiment we're doing gives you 3. Trying to see which one it gives us. I don't think for the first part, I don't think it I don't think it gets, you have to do the unknown one. Let me see. No, I think you just measure the different materials, do 3 trials, and give the densities. So that part is fairly straightforward. So any questions about how to do this particular part of the lab?
So do we need a table for each material?
You just have one table. You can do it any way you want. I would generally just put everything in one big table. You could have 5 tables if you want, although generally it's just easier to do it in one big table. But yeah, all your data should be there.
Professor, do you want us to show how we convert from grams to kilograms, like the little?
Yeah, you give like in your data portion, in your results part. So your results would be the data and an example of a calculation. So if you're presenting your results in grams per milliliter, you would show how you converted kilograms to grams and liters to milliliters, and then how you did the calculation of density. Yeah.
Okay. And then on this first lab, will you give us like little notes, like, hey, correct this for next time? For the next time?
Yeah, definitely.
Okay.
Yeah, that's the whole point.
Okay, thank you.
Yeah, and you'll see that I may not be super quick at grading these. I'm a little better during the fall and the spring than I am in the summer, because the summer we're just overwhelmed. But yeah, I'll try and have them all graded like a week after they've been submitted. Like a week after the due date, hopefully I'll have all, if not most of them, graded. Okay.
Do you want 3 trials for the unknowns also, or just the one?
I don't. In this particular example, I don't think you're called on to do the mystery one. That's the next lab.
There's a table B, and it says the density of unknown objects. It's right under the density calculations of the 3 trials.
I think that's for the second lab. Or is it? No, you're right.
Yeah, it's under the lab.
Is there E? You're right. So, yes, you're right. I'm sorry. Yeah, I'm obviously I'm getting them confused. Yeah, there's 5 mystery objects. So yeah, so that's part of the. Yeah, you're right. And so since there's 5 knowns and 5 unknowns, the idea is that you'll be able to figure out what A, B, C, and D actually are. So for instance, if you let's take D. Let's move this over here so we can put D. There we go. So just take D, put it up on the, so it gives you 3.1, that looks familiar, 3.1 kilograms. And we don't know what its volume is, so we dunk it in the water. And you can see that it's just floating, but because it's floating, we need to push it down. So it's 3.1 kilograms, but its volume is 3.38 liters. So then we calculate the density and then refer back to what had that density. What do you think this is? What does that look like to you? It should kind of look familiar. What do you think D is?
Ice.
It's ice. That's right. it's ice. You can see because it's almost the same density of water. It's just slightly less. And we'll actually learn why that is. It's because of how water molecules interact with each other in the solid phase and the liquid phase. Actually, they form a slightly different structure when they're a solid, and the molecules are moved a little further apart, which makes it slightly less dense. So the ice floats on the water. But you can see, just like an iceberg, people always say, you only see the tip of the iceberg. Well, that's what that means. So, 95% of the ice is below the surface and you can't see it. You only actually see the tiny bit that's on the top, because the density is almost exactly the same as water. It's only slightly less, like 97% of the density, something like that. Right. So yeah, thanks for correcting me on that. I thought we were only doing the unknowns for the second part. Yeah, there is a first part and the second part.
Are we doing just the first part today or all of it?
Well, I mean, basically during the lab session, I'm just basically here to introduce how the lab works. I'm not going to do the whole thing because that's for you to do, right? But I'm sort of to clear up any questions you might have and how to do it. So in this instance, you figure out what the densities are of the 5 objects that are given. This is styrofoam, wood, ice, aluminum, and what's the 5th one? Anyone remember what it was?
Out of the table underneath mystery.
Brick. It was brick. So you figure out what those densities are, and then do the 5 different mystery ones, and that'll go. So this should only take you about 20 minutes to do. It'll take you more to actually like run through all the calculations and everything, but actually getting the data, it goes really, really quickly.
I mean, part 2 after the mystery.
Excuse me?
Like if you scroll down below the mystery, there's like part 2 of the lab. Are we just doing part 1 or the whole thing?
I didn't get the question.
Like if you scroll down some more, there's the part 2.
Yes.
Why do some objects sink and others float? We also do that today, right?
Yes, we're going to go to that. We're going to go to that next. I just want to see if there's any questions about this particular simulation before we go to the second one. Does anyone have any questions on what you're going to be doing here?
How can you combine all of the materials into one table for table A? Because we have to do it.
Well, you can either make 5 tables, or you can put them all in one. It's up to you.
Is there like a certain format to put them all in one?
Nope, you can have any format you want.
Okay, thanks.
Yeah. So yeah, basically, I would probably just have, my 3 trials for object 1, and then my 3 volume trials for object 2, object 3, object 4, object 5. So you'd have, 15 columns, and then just put all your data in there. And then at the bottom, you'd have your 15 columns, and the last column would be the density, your 3 different densities for each one, and then in the middle, give the average. That'd be your last part.
Right.
Your last row would be the average density. And that's what you would use to go forward. Excuse me.
Sorry, I was late.
Oh, no worries. No worries at all. So is everyone's clear then on this particular one? We can go to the next site.
By any chance, are you going to publish like an example of like, so we can kind of go based off of something?
Yeah, that example I just showed you is published in Canvas.
Okay, I wasn't sure. Where can I locate that? I'm having trouble.
It's in the very first, let me go. Whoops. should be able to see Canvas, Canvas, Canvas. Okay, here we go. So home, you've seen the Canvas shell now?
Yeah.
So it's the very last one under Welcome to Chem 210. It's good example of a lab report.
Oh, perfect. Yeah, I just found it.
Yeah. And you can download that. Yeah, I had to change it because I realized the person who wrote it put their name in 3 different places, and so I had to. I only removed it from 2. It's like, oops. So I went in and grabbed it. Yeah, basically that's just. I mean, obviously it's not the best lab report I've ever seen, but it gives you a good idea of like how you could either. I mean, this person did not put everything on the computer, and that's fine. She like wrote some things out by hand and then copied and pasted that and put that in her report, and that's fine too.
Okay.
But everything was clear. Everything was I could read. All the different sections were there.
Okay. So we don't have to handwrite it like this person did, right? We can do it on.
No, I would prefer it if you didn't. But if you can't type all that, I mean, and you want to write it by hand, that's fine.
Okay.
But write it in pen, not pencil. We never, ever write in the lab in pencil. In fact, if we were in the lab right now and you were like even writing your data in pencil, I would come over and give you a smack, because we do not write in pencil ever, because you will get in trouble if you become a scientist, and I'm certain all of you are. But even if don't become a scientist, even if, like say you work in a hospital, you can't write anything in pencil, because let's say a patient dies because you gave them the wrong dose of something. If that patient record is erased and replaced with something, you're going to prison, and there's no way around it. So it has to be written in pen, and if there's an error, it has to be crossed out, initials made, and the date that you changed it. And that's the only acceptable way of collecting data in a laboratory situation.
If the patient dies, you're also going to go to the
not
jail.
if it was an honest error.
Oh, okay.
What if the drug company sent you the wrong dose by mistake? And so you gave that patient 1 milliliter of the solution that was provided, but the concentration of that was 10 times more than it should have been. And so you didn't make the mistake, the drug company made the mistake. So if you did not keep good records, you're going to prison, and the drug company is getting off scot-free. That's why it's so important to have good records, and why it's so important to write them in pen, because if you wrote that thing in pencil, some might think you're trying to avoid something. It's sketchy. If something's written in pen, it means, I wrote that and I meant that to stay there. So we never ever write in pencil. It's a particular bugaboo of mine, because I've had the government go through my lab books before, and so they look for that kind of thing. They want to make sure that all of your data has been correct, is there. If you made a mistake, that's fine. People make mistakes, but you cross them out and you change them. So if you made an error, let's say you made an error in your lab notebook, in your procedure, and then you realize before you did the experiment, oh, duh, I'm not supposed to put 10 mils. I'm only supposed to put 1. Idiot. If you just erased it, you'd be in trouble, because they would say, well, I don't know what you did here. Is this the actual volume you use, or is this the one you changed to save your ass afterwards? But if you cross it out and change the 10 to 1.0 and then put your initials on it, that means that you changed it before you actually did the experiment. So it's important. And another reason not to use pencil is because when you take a picture with your phone of your writing in pencil, it's not as clear as it is with pen, and so I can't read it as well. And the other thing is if you write in a notebook in pencil, and you're opening and closing pages, the pages are rubbing against each other, a lot of that graphite gets transferred, and so it gets smeared and makes it more difficult to read too.
If you drawing a graph, you also use a pen.
Mm-hmm.
Okay.
Yep. Yeah, hopefully you use your computer to draw graphs. We're going to do that later. But if you do have to hand draw, at least use a ruler, because I've had people just freehanding graphs, and that's not acceptable. You're not going to get any precision that way, because we make graphs for a reason. We make graphs not just to show the relationship between two things, but to make predictive estimates of what a result would be, and you can't do that with a free-handed graph. All right, let's go to the second part. So our second part, part 2. Here's our second simulation. You can just click on that. Allow. It's loading it up. So there we go. Hopefully, could everyone see this particular example?
Yes.
Can everyone see this one?
Yes.
Mm.
Yes.
All right, good. So there's a little description, what's going on here. When an object is placed in a fluid, you get buoyancy forces. Buoyancy acts against the weight of the object and pushes it up. And so the denser a particular liquid is, the more buoyancy it produces. So if we have water with a density, what is the density of water anyway? Anyone tell me what it is?
1.
1 grams per centimeter cube.
Yes, or mil. A mil is a centimeter cubed. It's the same thing. But yeah, why I said is because you gave me a number. And remember, a number without a unit is useless.
Is nothing.
And
It's
that's
worse than nothing.
that's
Just
4
it brings-
degrees
it
Celsius.
Yes, at 4. If as we heat the water, it'll become less and less dense, because as we heat the water, the temperature, we will learn, is actually a measure of the kinetic movement of the molecules. And so the higher and higher the temperature, the faster and faster the molecules start moving, and the further and further they move apart. So the density of water to almost boiling is less than it is at 4 degrees. But we're going to assume the density of water is 1 gram per mil. Right, so what we're going to do is take the mass of different things. So we'll just take some wood down here and put it on, get down there. There we go. So we take the mass, 3.30, and now remember, all of those masses are going to be, all of those digits in the mass are going to be significant. So we've got 4 significant digits here, okay? And then you drop it and that is the volume of water it displaced. Now here is where you're going to have to make a judgment on what the unit should be. So what do you think that volume is? You can see that this is slightly different than the graduated cylinder we had before. The graduated cylinder we had before just had gradations, had 10 gradations between each mill. And we can see this one, oh, this one has 10 as well. You see there's major and minor ones. But there's 10. The other thing that's a little tricky is that this would be the view you would get. This would be the view you get if you looked above the meniscus.
15.70.
So they actually don't give you the best view. The best view would be, you could see, because you can't see the meniscus here, can you?
No.
You can't. So this isn't a particularly good simulation, and I need to find a better one. But it gives you, but when you write your lab report, this is going to be what? A source of error. This is a source of error. So this should be in your report, that you weren't able to measure the volume accurately because you were not able to put your eyes directly at the sight level of the meniscus. Like bad computer program.
Excuse me.
Yeah.
How did you know it was above again?
Oh, because if you were at the exact level of the meniscus, what you would see would be this. So this would be the graduated cylinder, and this would be the water. And so we would be able to see this meniscus here. But here we can't see it. We can't see the meniscus. So we must be above, looking down. It looks, by looking at it, you can see that we're sort of above the level and looking down slightly. So it's really hard to see where the meniscus is. So we're going to have to, make some estimates here. So what can we say? We can say that it's more than 15. Whoops.
Okay.
Here, let me go back. So we can say for sure it's more than 15.
Is
So
it
it's more than 15. It's
15.16?
less than 16. It's more than 15.2,
5.
4, 6, 8. It's around 15.6.
60.
So what would we say? What would you? That's probably, I don't know. What would you say it would? What would you give as a volume?
Okay. One.
10.60.
Yep.
15.62.
0.
60.
Yeah.
Yeah. Yeah.
That's very good.
That works.
15.60.
That works for me.
I have a question.
Yes.
Or when you said when you were talking about the source of error, how would you explain it to be super specific and not overword it and make it complicated?
Wow. You're already criticizing your own writing. Yeah, I mean, you don't. Basically, what I've found with the way students write too much when they don't actually understand what it is they're writing. And so basically what they will do is explain the same thing like in 3 or 4 different ways and just go on and on and on because they don't really know the point of what they're getting at. In this particular situation, there's a problem with reading the volume because your eye level is not at the meniscus. That's it. That's all you have to explain. And so, so just explain, since my eye level is not at the level of the meniscus, my estimate of the volume will be affected. You don't have to say it's going to be more, it's going to be less, because you don't really know. Because you just know it's going to be affected somewhat. And that's it.
Okay.
Then you're done. Yeah, so but what a student who didn't understand that would probably just go on and on and on about what the effects of it was too high or if the effect was too low, and what a meniscus is, and like the forces forming a meniscus, and it's like yeah I'm not interested in any of that. How come you can't read? How come you can't measure the volume accurately? That's it. Just explain why the volume might be inaccurate.
Okay.
Yeah. So we should have, even though it's not going to be super accurate, you should get 4 digits for the volume, because we know it's not 15, we know it's not 16, and then you have the gradations 0.1 in between. So that should be fairly precise too. It's just that it'll be difficult to get a really precise estimate of this digit here. It's going to be a little iffy.
My confusing is why this is a computer. Why would that?
Why would it do that?
That's
a good question. I don't know why it would do that. Probably so, it can make me look clever and saying this is not the right way to do it.
Well, the computer programmer is not a chemist, so.
Yeah, they're probably some horrible physicist or even worse, an engineer. Oh my God. Yeah, I mean, basically, I think It might be. I mean, if they were really clever, it might be so we could actually talk about sources of error. I don't know, but it's based on what we were just talking about. It's pretty apparent that we can't see. Well, we talked about meniscus before. It's pretty apparent we can't see one this time, and so that's going to affect ourselves. So if you were, what was our mass? I can't remember what our mass was.
13.30 gram.
So it was. Let's write that down. So our mass was it 13.3?
Yes, sir, gram.
30?
Yes.
Okay. And our volume, what were we going with? 15.60?
1560 milliliter.
Milliliter. So what is our density?
Okay, this is wood, yeah?
Yeah.
0.85256. I think that's enough. And we should run
Or
it.
maybe it's too much. How many significant digits should we have? Remember that we have to have units. If you just give me a number,
Grams per
I'm going to be
minute.
very upset. So how many significant digits should we have?
4.
4. So what should our answer actually be?
8626.
6, that's right. So we get rid of this 6 and make that a 6. So 0.8626. So did the object float or sink? What do we think?
Float.
Okay. Based on what?
Based on the
Density.
Based on the density being what?
The density of wood is less than the density of water, so I believe it should be floating.
Right.
And we know wood usually floats. So
Right. So we'll put usually, but not always.
I agree.
So float. Watch what happened. Yeah, we did. Yeah. So so you do each of those, and I think so. Then you measure the density. Make sure you get the proper amount of significant digits. Obviously, that's super, super important. And then I think it asks you to, mass, volume, density. And then remember, are we going to do each of these once?
excuse me.
Yeah, go ahead.
It doesn't matter if it's float or sink. It's used the same method, right?
Yes. Yeah, we're just basically determining. We're just going to make an educated guess as to whether it will float or sink based on its density.
Okay.
Professor,
Yes.
is there a list of densities, or are we just like searching on Google to find the density of wood and aluminum?
Well, there's no density of wood. If you look up density of wood, they're going to ask you what kind of tree.
I agree. I just looked it up.
That's
because the wood we did in the last experiment was like 0.4 grams per mil, and this one 0.86 grams per mil. So obviously, it's soft woods are less dense than hardwoods, and so it really depends on the wood.
I have a resource says a good wood would have a density between 0.2 to 0.75 grams per millimeter.
Yeah, but what does it mean by good wood? Well-behaved wood? I don't even know what that means.
A good wood to make things.
Make things, yeah. Because things like ironwood is really dense, and it's like I think it's more than 1 gram per mil, and so just trying to cut that basically destroys saw blades. You need a special saw blade to cut that because it's so.
Yes, I was just
so damn dense.
translating from Chinese to English directly, so I said good.
I see. Yeah, so I mean, including like the plastic. If you look up what's the density of plastic, it's going to ask, well, there's about 1 million different kinds of plastics, and even the same plastic can be made with varying density. like polypropylene or polystyrene, can be
Um,
made in a lot of different ways.
But I mean,
So-
for this lab, when we're trying to find the density for the unknown, do we
Mhm.
have like a list we're gonna be comparing it to?
Oh, we're not doing an unknown. Is there an unknown in this one? I don't think.
Oh no, I guess I was talking about for because you asked the density of something else, and somebody gave the density, and I was just wondering where they got that from.
We do the math between the
Yeah,
weight and the
that was the
volume.
last one. Yeah, that was the last. We base the unknown should be one of the five. One of the five. So the last experiment, the
Oh,
last
okay.
site was one of. There's 5 knowns, and then there's 5 unknowns, and they should match.
Okay.
But in this instance, yeah, I mean, obviously, wood from experiment 2 is not the same wood from experiment 1. And the same thing is true here. You can't look up plastic. You can't look up cork. You can't even look up steel because there's so many different. Is it stainless steel? Is it carbon steel? They all have slightly different densities. Clay,
I think
a
for
lot of different rubber, candle, they're all going to be different. The only thing you could actually rely on is aluminum. Should give you like 2.7 grams per mil, but everything else is going to be just some kind of random number.
I think for substance, is that substance? The density is stable, not constant, right?
Density is constant for a
For pure-
particular for one of
For-
these substances. However many times you measure it, you should get the same thing. But plastic doesn't refer to just one thing. It refers to. Adriana, you had a question before I forget. You raised your hand there. Adriana, you still with us?
Oh, yes, sorry. I had a question. Where in the report do we write our source of error?
That should be in your discussion.
Okay, so when we type up or write up our discussion,
Yeah.
we should. Okay, thanks.
Yeah. So results are the data, like your data table and graphs, if there are any. Those are your results. And then in the discussion, you take those results and explain them. So yeah, so if you had sources of error in getting that data, then you would explain that in your discussion.
Okay, thank you.
Yeah, no worries. So any questions on how to do this part? This part's fairly straightforward. And actually the whole lab's hopefully is fairly straightforward. Just a lot of calculations. Yeah.
The word I was.
Do this 3 times?
Yes. Yeah.
But even though it's a simulation and the results are going to be the same, we're going to have to do this 3 times.
Yeah, well, it's not going to really take you much longer.
Okay.
But yeah, I mean, you make a good point. I mean, in the last experiment, we want you to change the size, so you'll get 3 different results, but with the same average. So yeah, actually, with this one, you could probably just do it once, and that'd be fine. Because yeah, you're going to get exactly the same results. You can't change the size of any of these things. So yeah, it's true. You don't really need to do this one more than once.
Sometimes it can't be done for 3 times, right? I mean, can't.
Well, I mean, that's not a particularly good experiment. I mean, if you don't have enough materials to do the experiment 3 times, then don't do the experiment. Make sure you. That's why, like in the lab, we would make sure that we had enough materials to do everything at least 3 times. Because some of the experiments we would do in person in the lab, like, if we're determining the concentration of something, or if we're determining the mass of an unknown gas or something like that, if you did it 3 times and one of them was clearly, different than the other 2, we'd ask you to do it again. So then you'd do it 4 times and have 3 of them to measure. So usually, when we're doing an experiment, for reals, you make sure that you have enough materials to do it at least 4 times.
Are the questions under table B and table C the part of the discussion questions?
Yeah. Mhm.
Okay.
Yeah.
Thanks.
So yeah. So in your discussions, you try and you'd answer those. Yeah.
So there's a pre-lab section, a post-lab section, and a discussion section.
Yeah. I don't think there was much in the pre-lab this time.
Well, that was one question.
Yeah. So yeah, you can just. And I think we just sort of and that was just the cylinder, right? And I think we just sort of answered that one together as a group. So yeah, we don't even really need to include that one, but all the post lab questions should be in there.
Okay. Let's continue.
All right. Any other questions about? So we can either do another one of these. We can talk about lab reports, or we can go and enjoy this beautiful smoky day. Anybody have any other questions about either lab? We can go back to the other side.
Excuse me, Professor?
Yeah.
I came in too late, actually. I was waiting to the course to show up in Canvas so I can get the link and get into the class. So I don't know if you mentioned something really important at the beginning.
Were you able to add
Thank
today?
you. Yes, sir.
Excellent.
Thank you so much.
No problem. So what question did you have?
My question is, if you mentioned something earlier during the meeting here in Zoom, I didn't get this information, so that's what I'm asking for.
This video will be posted tomorrow, so you'll be able
Tomorrow,
to,
awesome. I'll be
the whole
watching from
thing.
the beginning. Thank you so much.
Yeah, a lot of people go over the video, especially when either they missed the first part of it for whatever reason, or it's just it's just too damn confusing and I'm babbling like an idiot. They could slow it down and go over it a little more slowly.
Oh,
I agree.
Yeah, either one. Flip a coin. Question. Oh man, now you're both backing up. One of you had a.
Did you receive my email for the 250 2544 question?
I haven't checked yet.
Okay.
I was walking the doggies at lunchtime. Nicholas, you had a question.
Yeah, sorry, I'm taking a few classes. Did you say you have an SI for this class?
SI meaning
like
somebody like a mental instructor,
tutor.
Yeah, just a tutor.
Yes. There's a link to it in Canvas. There's damn it, I don't have his name in front of me right now.
Person.
Yeah. But send me an email. I'll send you the name, his name, his email address, and there's a schedule in Canvas for everybody who's tutoring the different classes. You're not just if he's unavailable at some particular time. I think there are other tutors for Chem 210 as well.
Okay, thank you.
Yeah.
So,
any questions from the chat? I should.
I actually posted it in discussion that said I did something wrong for last recitation. That
no!
I put
so that's one thing I can do. I can just sort of just keep this going. If you guys want to, talk among yourselves, and you could like work on recitations. You could do the lab together. Do you want me to do that?
No, I just point out for last recitation for last question. I gave the digit the number for the rate for the diameter instead of the radius.
You know who else did that? I realized that when I had made a key and sent it out to my last class, and I had a look at the key, and I realized that I made the exact same mistake. Because when I was grading them, everyone kept getting a different answer to the one I was getting. It's like, what the hell? And it's like, oh, right, because I did it wrong. Yeah. So that's going to happen, you know.
I mean,
so that is
that number was given by me, so I said I made this mistake.
Yep. Yeah. No, I made the same mistake, and so that is why, if you show I always say, if you show your work, because I always, you know, when I make the key, I, you know, show all the steps that went into doing it. You're going to get 90% of the points because you just made a dumb error.
Mm-hmm.
You know how to do it. You just made a dumb error, and you know, we shouldn't take away too many points for being dumb, because, like, you know, all of us are dumb. So, you know, if it's more important to know how to do the question than getting the question right. That should be, you know, true in life. It isn't always, but it's true in this class anyway. Okay. So what if there are no more questions, would you prefer I just sort of just let the meeting keep going, or all of you just want to just do it on your own?
I have a question.
Sure.
For the recession that is due in another 2 days, what is the recession? Is that just
recitation? Like, we're in a recession. That's a whole different thing. So the recitation is in under Canvas, under recitation sessions, and it's the first worksheet. Actually, I can since you got my screen up, I can take you to it right now. So let me clear the drawings. So here's the Canvas page, and we just scroll down to recitation work sessions. Recitation 1, Intro to Chemistry. We just click on that, and boom, there it is. So if you can print it out, that'd be nice. You can just download it, print it out, and then write right on it. If you don't have a printer or don't want to print or whatever, that's not a problem. You can just read the questions right here and just answer them. Just write them down on a piece of paper. Make sure you show all your work, and then just submit it.
Does that also have to be in pen?
Yes. Okay. Well, have to be. I would prefer it. I mean, if you write it in pencil and I can actually read it, okay. I mean, it's easier to transfer the image to computer when it's in pen. It's just clearer. Unless you've got the world's darkest pencil, then that's fine. But lab, never should have a pencil for a lab report. Ever, ever, ever.
Got it.
Yeah.
And okay. I also have a question about
go ahead.
The site that we use for the homework. I've been
site for the homework. What do you mean?
Is that there's a single course homework only access code?
Oh, you're talking about Sapling?
Mm-hmm.
I haven't assigned Sapling.
Okay. Evidence.
Yeah, I haven't assigned it. So if you've bought it already, you can get your money back. But I haven't assigned it. I'm still discussing with the other faculty of whether or not to assign it. I haven't in the past. But you know, if people would find it helpful, then I mean, it certainly doesn't hurt. But yeah, I don't think I'm going to include it as far as a grade. But I mean, it's good practice. You can also do. There's lots of practice. I've included let's go back to the home. I've included the questions in the manual, in the textbook. If we go down to different chapters, we scroll all the way down, like chapter 1. There's the slides, and then there's the textbook resources for chapter 1. And under chapter 1, I show you where in the textbook the pages are. So if you want to read rather than listen to my lunacy, there's where the pages 9 to 54 in the textbook, which is also free. is the read that part. And then the problems is a problem set from page 54 to 65. And then you have an answers for all the odd number questions at the end of the book. And I show you where that is. So if you want questions to practice with, I just suggest doing the ones you already have that are free.
Okay.
And so if I assign any additional homework, it'll probably just be those questions. Yeah, I still don't like the idea of you guys having to pay for extra homework. I know, kind of a scam.
And this
but if any of you have already paid for it and you get something out of it, then yeah, by all means, go for it. I think it's helpful because it shows you can give your answer, then it says no, not quite, and then you put a different answer in. It says, hey, you're getting close, and so yeah, a lot of people like doing that.
And this is from the PDF textbook you have on there.
Yep. Mm-hmm.
Okay.
Yep. And I'll be honest, it's not the best textbook in the world. There are mistakes in it, but hey, you get what you pay for, right? So it's free. There's nothing glaring in there. There's nothing like Marie Curie was from a different planet or something. But it's there's a few little niggling things in there that are a little odd, but nothing severe.
Where did you come from here? Could you click that again?
So go to the Canvas page. So when you open it, you should actually. Where's my student view? All right, so this is what you should see when you go to that page, right? Mm-hmm. So then we scroll down to the chapter. All the way down. So chapter 1 context.
Oh, I was just saying the textbook was too large yesterday when I.
Oh, it is. It's huge. Yeah, but that's why you should download it. The textbook is right here.
Yeah, I was trying to download the textbook yesterday.
Yeah, it's 206 megabytes, so it'll take a while. But you should have it. I mean, yeah, because it's good for studying. Like I said, it's also good for the problems, because I mean, I take a lot of test problems out of there. So versions of of the problems you'll do in the textbook are eerily similar to things you'll see on tests.
So under the chapters, they are the same thing, but you're dividing already dividing them in chapters, right?
No, I mean, I don't follow the textbook exactly, because I think chapters 3, 4, and 5 just go over the same material sort of over and over again. So I sort of skip right to 6. And so my chapter 3 is the book's chapter 6, but we're not going to completely ignore it. It's just that a lot of the stuff we're going to do, like stoichiometry and balancing reactions and stuff like that, we're going to just do anyway. And if you want extra reading on it, I will, point you in the direction of the textbook. But it's just, I think it sort of hammers the same points home over and over and over. It's like, we get it. That's because if there's 19 chapters, so obviously we can't do them all. So I try and go to the ones I think will be most beneficial for going on to the next class.
Okay.
Can we do one example real quick on finding the initial volume, final volume, and the actual volume for table A?
Oh, okay.
Thank you.
Table A. Good old table A. That's fine, table A. So online lab, table A. Yes, initial volume, final volume. So when we go to, so here's the initial, this is the initial lab. We pull that out. So this is the initial volume right here. That's the initial volume of the water before I put anything in it, right? So in order to calculate the amount of water the volume of the water that was displaced, we need to know what the volume of the water was before the object was added and after the object was added. And the difference is the volume of the object. So the initial volume is always going to be 100 liters, 100.00 liters. And then when we drop whatever it is, I think that was the brick. No, it was the aluminum. We dropped our cube of aluminum in there. Then we look at the volume. That's 101.57 liters. And so the difference is the volume of aluminum.
Okay.
Yeah.
Thanks.
Yeah, basically we're just sort of going, what I was trying to do is to make it as similar as to when we were doing the lab in person, because not everyone is going to have exactly the same volume. So you would have a graduated cylinder, and some people would fill it to 30, and some people would fill it to 35, and other people would fill it to 25.6 or whatever, and then they drop their object in and get a new volume. And so the point was, it didn't really matter how much water you had in there, as long as you had a larger volume than the object, And so it didn't matter what it was. It's just because the difference is what we're looking for.
And then our only calculation would be converting it from liters to milliliters, since the table asks for milliliters.
Well, two calculations. Calculating what the proper units are and actual calculating the density. So
yeah, okay.
Yeah. Anyone else? Before I lose my voice entirely. Man, it's just so damn smoky today. Okay, so, go ahead. Nope, this is the time to ask.
So for the 3 trials, let's say we're doing aluminum. So we have to change the mass, right? Like for all 3 trials, they're not going to, because otherwise we're going to have the same.
Yeah, you just do the same thing 3 times. Yeah, so you want to change the mass, have 3 different masses and 3 different volumes. And, hopefully you'll get the same density. Pretty sure you will. But yeah, you should. The whole point is just to show that mass is an extensive property. Volume is an extensive property. But when you divide one by the other, you get an intensive property.
Okay, for some reason I thought that it was always going to. I thought it was going to be the same thing, and I said, "Wait, what's the point of doing it 3 times then if we're going to get the same answer?" I don't know.
I think it's 9 times for 3.
Right.
Yeah, totally 9 times because.
Well, you're doing 5 though.
So
there's 5 different things. There's
15.
Yep. There's styrofoam, wood, ice, brick, and aluminum. So there's 5 objects. You do each one 3 times with 3 different masses. So yeah, it's not going to take you very long to do them. Just collecting the data is going to be no time at all. Just means you're going to have a really big data table.
Okay.
Yeah.
And you said we can make as many data tables as we want, right?
Yeah.
If
I don't care.
Okay.
Make sure. Yeah, you can make a data table for each one if you want. That's completely fine. But what I would say, make sure that each one has a title. That's really important. Data tables have to have titles, and in the data table there has to be units. So like generally you don't write the unit in every square, but what you would say is like mass, comma, grams, or mass, comma, kilograms, and then you'd have the numbers in each square. So but you have to have units. Because we all know a number without a unit is very sad indeed.
So when you put the units right next to the mass or like the volume, let's say, you don't have to keep putting it right next to your answer in that same graph or data?
Nope. Okay. Yeah, so that, because then it's kind of looks messy. It actually looks nicer when you don't do that. So for instance, So if I had volume liters, so this is and then I make my graph. These are my 3 different measurements. So I would just put like, 1.03, 2.06, 312. And it's assumed that all of these are in liters because you've told me in the very first column, you tell me 2 things. These are the volumes and this is the unit I'm using. So then you don't have to keep telling me, I got it, it's liters.
Okay.
Yeah. So actually it looks better if you don't put the units in. If you don't give me a unit, then if you just had volume on the side, then you do have to include liters each time.
Excuse me.
Yep.
But that makes a problem that what if you accidentally recorded a different number for units, like you put liters for volume, liters for the first one, and then you put 312 for the last box, and
so you had like milliliters instead of liters.
Yeah.
Well, then you're gonna fail the class. What can I tell you?
Okay.
Yeah.
I mean,
you just have no choice but to fail you.
Okay.
Yep. I mean, what else can I do? I mean, it's just the way it goes. Yeah. I mean, if you made a mistake like that, it'd be pretty obvious that you'd switch, because if one was 1,000 times, because if you had like, 1.03, 3.12, and this was 2060, it's pretty obvious that this one is in milliliters. So I just put a note on it saying that's in milliliters, isn't it? Yeah, that's it. It wouldn't be a big deal. But if you changed it for some reason and then you put milliliters in there, I'd wonder why you did that. I mean, if you put on the side in the first column that you're going to be putting all your units in liters, why would you switch in the middle? It doesn't make a whole lot of sense.
Because maybe you are measuring water first, and then you measuring a gas.
Okay. Well, you probably wouldn't have those in the same data table. Or maybe you would. I mean, yeah.
Yeah. Okay.
Okay. It would appear someone's at the door based on the barking. Anyway, so any other questions before I have to go and muzzle some dogs?
Professor, can I do the chart? You might have gone over it. Can I do the chart in Excel, or does it have to be done by hand?
Okay, sorry, I couldn't hear the first part.
Can I do the chart in something like Excel or Sheets?
Oh, of course.
Okay.
Yes, but you can't export sheets. You can't put your whole report in Sheets and then basically send me a link, because then I can't open that. So what you should do is make your chart in Sheets or Excel or whatever, and then export that to something I can then read, like a PDF file or a Word file or a image file or something like that. But but some students have tried sending me links, to their Google Charts page, and then I can't open it, and then I can't open it, and even if I did get permission and can open it, I can't leave any comments on it. So it's best for us both if they're converted to something I can actually write on.
So it shouldn't be .xsl.
Yeah, if you want to do your whole report in Excel, that's fine. I can, I think right now I've got .doc, .pdf, and a couple of others. But yeah, if you want to do the whole thing in Excel, that's fine. I mean, Excel's not really great for actually writing in, but it's good for charts and such. Okay, is everybody good? dogs have quieted down for a second. Okay. Any other questions? Yeah, you've probably seen I respond to email pretty quickly because, you know, I'm at home. And so I will be having office hours tomorrow at 11, and class is on Thursday at 9:30. Okay? And we're going to start working on recitation number 2. Okay. Okay, I have to take these guys out apparently. Anyway, if there are any other questions, I'll talk to you guys soon. All right, bye-bye.